Paul Nurse won the Nobel Prize for Medicine in 2001. In this series of 5 lectures, Paul talks about how the great ideas of biology underpin our modern understanding of the living world.
Now, on the whole, us biologists tend not to talk too much about great ideas and grand theories. We leave those usually to the physicists. We biologists tend to be more comfortable with details, with particulars. What we like to do is to count things and list things. If I was a 19th century biologist, I would count the numbers of hairs on a beetle's leg. If I was an ecologist, I would count and list the species in a habitat. If I was a molecular biologist, which in fact I am, I would sequence genes and determine the proteins and RNAs that are in a cell. So we tend to describe things, but perhaps we don't focus enough on the great ideas of biology. But biology does have great ideas, and this evening I'm going to talk about 4 of those ideas, 4 which in my opinion are very important, and I'm going to point in the direction of a 5th which is yet to be fully formulated. I'm going to finish this talk with a 5th idea that I'm excited by, but which is not yet an accepted idea, but maybe in the future will become so. And that is to consider biology as an organized system. And the subplot here is to consider biology as a system that is managing information. Now, what am I thinking about here? What I'm thinking about is that we need to be able to explain the higher order phenomena that we associate with biology. Phenomena like homeostasis, that is, that an organism or a cell or a tissue maintains the status quo. Phenomena like communication, connections between cells and tissues. Phenomena like spatial and temporal organization. Think how different living organisms always have characteristic shapes and characteristic time spans. Those features are seen everywhere in biology, even in single cells. And I think we need to think about how we explain those higher order phenomena by translating the descriptions of the chemical and physical processes of life, which is what molecular and cellular biologists such as myself carry out, to translate those chemical descriptions into the management of information, i.e. how information is gathered, how it's stored, how it's processed, and how it's integrated together to determine specific outputs and bring about higher order biological phenomena. Now, this sort of thinking, which is not a new idea, as I shall point out to you, emphasizes regulation, networks, systems organization, emergent behaviors. Francis Crick said, and he always said interesting things, that in understanding biology, you have to follow three things. You have to follow the matter, you have to follow the energy, and you have to follow the information. And the most important of these 3 is information. Sounds rather biblical, I understand. Now, to illustrate the point, I'm going to give you 2 extremely well-known examples, because as I said, this is not a new idea, but it's a thinking I think we need to support. The first is the structure of DNA, the double helix I've already referred to. The double helix is a beautiful structure, but that's not really why it's beautiful for biologists. It's beautiful for biologists because that structure reveals that DNA is a digital information storage device. And understanding that tells us how DNA and why DNA is important for heredity. The sequence of the nucleotides encodes information. That information is digitally encoded. That information eventually determines protein structure, and that protein structure determines what enzymatic reactions go on, and that forms the basis of life's chemical machines. But it's only when the chemical structure of DNA is expressed in terms of information storage that it makes biological sense. And that's the point I'm trying to make. We translate the chemistry into information, knowing how that information is managed leads us to understand the higher level biological phenomenon, in this case, heredity. A second example. This is a governor from a steam engine. I took it actually in a boat in New Zealand. You know, there's something about machines. I don't know if you're like me. Any machine made before 1900 you can understand. And any machine after 1900 just gets, you know, increasingly more difficult. So we immediately understand what this does. When the vertical spindle rotates, those balls are swung out by centrifugal force, it lifts a valve, it cuts off steam to the steam engine. This is an example of a negative feedback loop. Here we have it restated in a form that we get more used to in biology. That is, a catalysis from A to B to C. If the appearance of C feeds back on the catalysis from A to B, it will switch off the production of C, maintaining the level of C in a homeostatic way. You can also have positive feedback loops which do exactly the opposite, which is that once you make C, it stimulates A to B, which actually throws a switch. It's much more like a switch rather than homeostasis. You go from one state to another. Now, this negative feedback loop was first described by Jacob and Monod in describing the lac operon, how you make transcripts and proteins from the lac operon. Now, you can describe the behavior of the lac operon in terms of chemical interactions, how the DNA makes the RNA, how it interacts with protein, how the protein catalyzes sugars. But it only makes sense biologically when it's abstracted into a logical regulatory circuit which is concerned with information flow, and in this case, it is a negative feedback loop where you're following the information. So these regulatory circuits, which we see in cells, can form feedback controls, switches, timers, oscillators, toggles, and generate complex networks which are important for managing information. And I believe it's important to translate the chemistry of these networks into the abstract modules processing information. One way of thinking about it is as an electronic circuit. Here we have gene names substituting for various components in the electronic circuit. Dennis Bray, in a recent book, has compared a cell to a computer in which the hardware of the computer is wetware, because of the fact we don't have wires within the cell, but the communication from one component to another is through a diffusible chemical. This means it's different in interesting ways, but the logic underneath it is the same. So we need to consider the cell as a complex chemical system or wetware acting as a logical computational machine of linked logical modules. Now I'm going to end my talk by giving a few examples of how this approach might illuminate the thinking of all of biology, not just DNA and not just negative feedback loops, but all of biology, particularly at the level of the cell, which is what I myself work on. And I'm just going to throw in a few random observations and thoughts here. The first is that the connections and networks which we see in cells have an uncanny resemblance to aeroplane route hubs. And here you see one in America, where certain hubs are much more important for others. And when you analyze the networks in living cells, this is what they look like as well. What this means, of course, is that Kansas City is rather unimportant, whereas Houston is more important, and New York would be more important. And this is rather like the sort of networks one sees in cells. A second thing that I'd like to draw to your attention is that we tend to think of linear pathways in biology, of causal rates of going from one step to another. But we have to put that aside because the lower diagram more explains how it works. Complex networks of positive, negative feedback and interactions. But our minds think more clearly in terms of linear pathways, but the reality is complex networks. But because we think more straightforwardly in linear pathways, we tend to like to reduce our observations to these linear pathways rather than these complex networks. When I say that, I think actually it's rather men tend to do that. I found this picture in a pilot's manual. The top explains how men think, simply on or off. The bottom shows the subtlety required in real thinking that we can associate with women's thought. And I think we need, in tackling this problem, to think more like women. Here's a network. We've got the lower, the green linear pathway. I want to introduce the concept of dynamics. If you imagine just sending a signal down the green arrows, you only have an on-off switch. That's all you can do. It's either on or it's off. Now introduce dynamics. Pulse information down that pathway, then the frequency of pulsing can convey information. This is a very, very important point, and I'm going to explain why in a metaphor. If we can pulse information down, then we turn this network from being an on-off switch like a traffic light into something where we can communicate much more elaborate information, and a metaphor is the Morse code, which is made up of dynamics. We move from simply saying yes or no to the ability to write the works of Shakespeare. Now, this is a metaphor, but do you think that living things are unlikely to have exploited the use of dynamics in signaling? I think not, but we barely yet understand it. One other point. All living things, I've said it before, have a structure in space and a structure in time. We need to understand how information can generate that. The Zhabotinsky chemical reaction defined by the great mathematician Turing is an example of how you can generate form across a structure. And one other final point here. We have to remember always that biological machines are not designed, and they're certainly not intelligently designed. They evolved by natural selection. And I'm going to explain why that's important, because if you have redundancies, which I'm going to explain is what will happen, then it means it's not easy to understand in linear causal pathways. This is John Harrison's clocks, the 18th century clockmaker trying to win the prize from the Admiralty for longitude. He started with the clock on top left. It didn't work properly. He therefore redesigned a completely new clock that looked quite different on the top right. That worked quite well, but wasn't perfect. He made another one, bottom left, eventually ended up with the one on the right, which did work. Each one he designed intelligently. Each one does not have within it the structures before, although maybe some of the ideas of before. If this was a living organism, you would still have in the bottom right-hand clock remnants from the top left-hand clock. This means that biological systems are extremely difficult to explain and to understand because of the redundancy that occurs there, because we still have remnants of things that we don't use. Now, I think applying thinking about information is going to be very, very powerful for biology in the future, but it's going to be complex and possibly counterintuitive. Until this date, biological explanations have tended to be in a common sense world. We work in a world that still makes sense in our common sense. But the complexity that I think we're going to see in biology may move us into a stranger world. An analogy here is the transition of physics, again at the turn of 1900, from Newtonian physics, which is common sense. We can all understand how billiard balls hit each other and bounce off each other, into stranger worlds. First with relativity. I don't know if you're like me. When you read these books about relativity, you think you've got it, and then you close the book and it's slipped away somewhere, you know? That's relativity. And if you think you have trouble with relativity, you take on quantum mechanics. 25 years later, it is utterly incomprehensible. I didn't realize that until my daughter Emily, who is a high-energy physicist, told me she didn't understand it either. She only understands it in terms of the mathematics, because that's the place where it makes sense. It does not make sense in our common sense world, and I suggest the complexity of life and the complexity of the networks we have to understand may take us into a strange and counterintuitive world. These are my great ideas. The cell, the gene, evolution by natural selection, life as chemistry. I think all biologists can agree that those 4 ideas are great ideas. There are other ideas that I haven't discussed that are also important. The 5th one that interests me, biology as an organized system managing information, I think is one that has already made its mark, and I think in the coming decades we will need to apply it more systematically to all biological phenomena, from cells through to populations, and as a consequence we will understand biology and life much better. Thank you very much, ladies and gentlemen.